Hey there, how was your day? Wherever you are in the world, whatever time it is, I'm glad you're here. Tonight, we're going to drift into something truly extraordinary. A gentle journey across the solar system to witness weather so alien, so magnificent, that it makes our most powerful hurricanes seem like gentle summer breezes. What if I told you that somewhere out there, storms rage for centuries, winds blow at supersonic speeds, and rain falls upward, made of molten glass? What if there are worlds where lightning crackles through clouds of sulfuric acid, where hexagonal hurricanes span entire continents, and where the very air itself would crush you like the deepest ocean depths? In this peaceful exploration, we'll visit each world in our solar system and discover the incredible weather patterns that dance across alien skies. We'll witness phenomena so beautiful and terrifying that they challenge everything we think we know about weather itself. But before we begin this cosmic voyage, feel free to comment your time and location below. It's always amazing to see when and where we're all watching from as we drift through space together. The visuals are here for you, but feel free to close your eyes, breathe deep, and let your imagination soar across the void. There's absolutely no problem if you doze off during our journey through the planets. Let your thoughts float among alien storms and distant worlds. If you find comfort in these gentle explorations of our cosmic neighborhood, I'd be grateful if you'd consider subscribing and liking this video. Let's begin our journey. Close your eyes and imagine stepping aboard a spacecraft that can take us safely to any world we choose. Feel the gentle hum of the engines as we lift away from Earth, leaving behind the familiar blues and whites of our home planet. We're about to witness weather systems so vast and powerful that they dwarf anything our world has ever known. Our first destination takes us closer to the Sun than we've ever been before. Welcome to Mercury, the innermost world of our solar system. Here, in this realm of extremes, we encounter weather unlike anything you could imagine. Mercury is a world caught between fire and ice, where the very concept of weather takes on meanings that would seem impossible on Earth. During the day, when the sun blazes overhead nearly 3 times larger than it appears from our home world, temperatures soar to a blistering 800 degrees Fahrenheit. The rocky surface glows like molten metal, and the thin wisps of Mercury's exosphere shimmer with particles blasted from the ground by the relentless solar bombardment. But Mercury holds a secret that makes it one of the most dramatically variable worlds in our solar system. You see, Mercury has virtually no atmosphere to trap heat or moderate temperatures. So when the sun sets on this strange world, something remarkable happens. The scorching heat that built up during the endless day begins to radiate away into the cold vacuum of space. The temperature doesn't drop gradually, like it might on Earth during a cool evening. Instead, it plummets with shocking speed, falling from those blazing 800 degrees all the way down to negative 300 degrees Fahrenheit. Imagine a world where noon feels like standing inside a furnace, but midnight is colder than anywhere on Earth, colder than the Antarctic winter, colder than liquid nitrogen. This isn't weather as we know it, but it's weather nonetheless. The rapid temperature swings create unique atmospheric phenomena that exist nowhere else in our solar system. As cosmic rays and tiny meteorites constantly bombard Mercury's surface, they knock atoms loose from the rocks themselves. These liberated particles create ghostly auroras and a thin, ever-changing exosphere that dances in response to the solar wind. Solar winds interact with Mercury's surprising magnetic field to form something that sounds like science fiction but is beautifully real. Plasma tornadoes spiral down from space, bringing the sun's own hot atmosphere directly to Mercury's surface. These aren't tornadoes of air and water vapor like we know on Earth, but swirling columns of charged particles that glow with their own ethereal light. Mercury shows us that weather doesn't require thick atmospheres or familiar elements. Sometimes the most dramatic weather systems are born from the interaction between raw solar energy and bare rock, creating a world where every sunrise and sunset brings temperature changes more extreme than any storm on Earth. As we leave Mercury behind and travel deeper into the solar system, we approach a world that represents the complete opposite extreme. If Mercury is a world of dramatic temperature swings, our next destination is a planet where the weather has created a hellish greenhouse so intense that it melts lead. Welcome to Venus, the brightest jewel in our evening sky and the most inhospitable world imaginable. From space, Venus appears serene, wrapped in brilliant white clouds that reflect sunlight so effectively they make the planet shine like a beacon. But those beautiful clouds hide a secret that makes Venus the most extreme weather laboratory in our solar system. Those pristine white clouds that look so peaceful from a distance are actually composed of concentrated sulfuric acid. The same corrosive chemical that can eat through metal floats through Venus's atmosphere in droplets so concentrated they would dissolve flesh in seconds. But here's what makes Venus's weather truly extraordinary. It rains sulfuric acid constantly, but not a single drop ever reaches the ground. The surface of Venus is so hot, so impossibly scorching, that every raindrop evaporates long before it can complete its journey downward. The temperature at Venus's surface reaches 860 degrees Fahrenheit, hot enough to melt lead, hot enough to glow red in the darkness. This creates a phenomenon called virga, where ghostly curtains of rain hang in the sky, never touching the ground, creating an eternal cycle of precipitation that exists only in the upper atmosphere. The atmospheric pressure on Venus is 93 times greater than Earth's. If you could somehow survive the acid rain and extreme temperatures, the pressure alone would crush you like being nearly a mile underwater in Earth's deepest oceans. Imagine the weight of a small car pressing down on every square inch of your body, and you begin to understand the incredible forces at work in Venus's atmosphere. But perhaps the most mind-bending aspect of Venus's weather is how the winds behave. At the surface, where the pressure is crushing and the temperature melts metal, the winds are surprisingly gentle, barely stirring the thick atmosphere, but rise up into the middle cloud layers, and something extraordinary happens. The winds accelerate to a ferocious 223 miles per hour, faster than the strongest hurricanes on Earth. These supersonic winds create one of the most puzzling phenomena in our solar system. While Venus itself rotates incredibly slowly, taking 243 Earth days to complete a single rotation, its clouds race around the entire planet in just 4 Earth days. The atmosphere is literally outrunning the planet beneath it, creating weather patterns that exist independently of the world they surround. Lightning flickers constantly through Venus's acid clouds, at least half as frequently as lightning strikes on Earth. But this isn't the familiar lightning of thunderstorms. These electrical discharges crackle through clouds of concentrated acid, creating a light show that would be both beautiful and deadly to witness. The greenhouse effect on Venus is so extreme that it serves as a warning about what can happen when atmospheric chemistry runs completely out of control. The thick carbon dioxide atmosphere traps heat so efficiently that Venus is actually hotter than Mercury, despite being nearly twice as far from the Sun. Once Venus's greenhouse effect began, it created a runaway cycle that transformed what might once have been an Earth-like world into the closest thing to hell that exists in our solar system. Venus teaches us that weather can be both creator and destroyer, capable of transforming entire worlds and creating conditions so extreme they challenge our understanding of what's possible. The weather on Venus isn't just dangerous, it's actively hostile to any form of life we can imagine. As we continue our journey through the solar system, leaving behind the acid-soaked hellscape of Venus, we approach a world that feels remarkably familiar, yet wonderfully unique. Our next destination is the only planet where we can step outside without a spacesuit, where liquid water falls from the sky, and where weather systems create the perfect conditions for an incredible diversity of life. Welcome home to Earth, our beautiful blue marble suspended in the cosmic dark. From the perspective of our cosmic journey, Earth's weather seems almost impossibly gentle and hospitable. Here, water exists in all three states naturally. Solid ice caps glisten at the poles, liquid oceans cover most of the surface, and water vapor drifts through the atmosphere as clouds that bring life-giving rain. Earth's weather is driven by the perfect balance of distance from the Sun, atmospheric composition, and the presence of vast oceans that moderate temperature and provide moisture for weather systems. Our planet sits in what scientists call the habitable zone, that narrow band around the Sun where temperatures allow liquid water to exist on the surface. But Earth's weather is far from boring. We experience everything from gentle spring showers to powerful hurricanes that span hundreds of miles. From delicate snowflakes that create winter wonderlands to tornadoes that can lift entire buildings into the sky. Our weather systems are incredibly diverse, yet they all operate within a narrow range of temperatures and pressures that make life possible. The abundance of water on Earth creates weather patterns that are both beautiful and dynamic. Clouds form as water evaporates from the oceans and rises into the cooler upper atmosphere. These clouds can take countless forms, from wispy cirrus clouds that stretch like brush strokes across the sky, to towering cumulonimbus clouds that reach into the stratosphere and spawn lightning and thunder. Earth's seasons are created by our planet's gentle tilt as it orbits the Sun, creating rhythmic changes in weather patterns that have shaped life itself. The monsoons that bring life-giving rain to billions of people, the hurricane seasons that redistribute heat from the tropics to higher latitudes, the winter storms that blanket continents in snow. All of these are part of the intricate dance of Earth's weather systems. Our atmosphere is a delicate mixture of nitrogen and oxygen, with just enough greenhouse gases to keep temperatures moderate, but not so much that we experience a runaway greenhouse effect like Venus. This perfect balance creates weather that is dynamic and sometimes dangerous, but always within the bounds of what life can adapt to and even thrive in. From our cosmic perspective, Earth's weather represents something precious and rare. It's weather that nurtures rather than destroys, that creates conditions for incredible biodiversity rather than hostile wastelands. Our gentle rains, our seasonal changes, Our moderate temperatures are not just pleasant. They're miraculous when compared to the extreme conditions we find everywhere else in our solar system. As we prepare to leave Earth behind and venture toward the outer planets, we can appreciate just how special our world's weather truly is. The next worlds we'll visit will show us weather systems of almost unimaginable power and alien beauty, but none will match the perfect balance that makes Earth a haven for life in an otherwise hostile cosmos. Our journey continues as we travel toward the red planet, where dust storms can engulf entire worlds, and where the weather tells a story of a planet that once might have been very much like our own Earth. Much like our own Earth. Mars beckons to us across the void, that rusty red world that has captured human imagination for centuries. As our spacecraft approaches this distant realm, we begin to see why Mars has fascinated astronomers and dreamers alike. Here is a world where the weather tells the story of cosmic change, where seasons stretch twice as long as our own, and where storms can grow so vast they swallow continents. The first thing that strikes you about Martian weather is the profound cold. With an average temperature of -85 degrees Fahrenheit, Mars is a world locked in perpetual winter. But don't let that fool you into thinking Mars is a quiet, inactive place. This is a world where weather operates on scales that dwarf anything we know on Earth. Mars experiences dust storms that make our most powerful hurricanes seem like gentle breezes. These aren't ordinary storms confined to small regions. Martian dust storms can grow until they encompass the entire planet, creating a globe-spanning tempest that can rage for weeks or even months. Imagine looking at Mars through a telescope and watching as the entire world disappears beneath a shroud of swirling dust, transforming from a recognizable planetary disk into a featureless orange sphere. These planetary dust storms begin innocuously enough, often starting as small whirlwinds called dust devils that dance across the Martian landscape. But under the right conditions, these tiny storms can grow and merge, feeding on the temperature differences between the dusty atmosphere and the cold ground below. As they expand, they lift millions of tons of fine Martian soil high into the thin atmosphere, where winds can carry the dust particles at speeds reaching 66 miles per hour. The dust rises to incredible heights, sometimes reaching 30,000 feet above the surface, creating towering walls of debris that stretch across distances larger than entire continents on Earth. These storms can persist for months, gradually settling as the temperature differences that fuel them begin to equalize. When they finally clear, they reveal a transformed landscape, with familiar surface features buried under new layers of wind-blown sediment. But Mars holds weather secrets that go beyond even these epic dust storms. The thin Martian atmosphere, barely 1% as dense as Earth's, creates unique meteorological phenomena that exist nowhere else in our solar system. Snow falls on Mars, but it's not the familiar water snow we know on Earth. Martian snow is made of both water ice and frozen carbon dioxide, what we call dry ice. This alien snow has been observed falling from clouds nearly 3 miles above the Martian surface. But just like the sulfuric acid rain on Venus, most Martian snow never reaches the ground. The thin atmosphere and low pressure cause the snowflakes to sublimate, turning directly from solid ice back into vapor before they can complete their journey to the surface. This creates ghostly curtains of precipitation hanging in the Martian sky, visible only to the sensitive instruments aboard our robotic explorers. Mars experiences seasons just like Earth, but each season lasts nearly twice as long due to Mars's more distant orbit around the Sun. These extended seasons create weather patterns that unfold over timescales that challenge our Earth-bound understanding of meteorology. Spring on Mars can last for 7 Earth months, during which the polar ice caps begin to sublime, releasing carbon dioxide back into the atmosphere and creating pressure changes that drive global wind patterns. The Martian atmosphere is thin enough that temperature changes happen with startling rapidity. During a single Martian day, temperatures can swing from a relatively mild 70 degrees Fahrenheit in direct sunlight to negative 100 degrees Fahrenheit in shadow. These extreme temperature variations create powerful thermal winds that sculpt the Martian landscape and drive the formation of those spectacular dust storms. Despite its thin atmosphere, Mars exhibits surprisingly Earth-like meteorology in many ways. Clouds form and dissipate in patterns that would be familiar to any meteorologist. Ice clouds made of water vapor drift through the Martian sky, often forming over mountains and hills just as they do on Earth. There are even jet streams in the Martian atmosphere, high-altitude rivers of fast-moving air that circle the planet and influence weather patterns across entire hemispheres. The seasonal changes on Mars are particularly dramatic at the polar regions, where vast ice caps made of frozen carbon dioxide and water ice advance and retreat with the changing seasons. As spring arrives at each pole, the warming temperatures cause the dry ice to sublime directly from solid to gas, creating geysers of carbon dioxide that shoot hundreds of feet into the thin atmosphere. These geysers carve dark streaks across the polar landscape, creating patterns that change and evolve throughout the Martian year. Mars also experiences phenomena that we're only beginning to understand. Mysterious recurring slope lineae appear on Martian hillsides during warm seasons, dark streaks that flow downhill and suggest the possible presence of liquid water, even if only briefly and in very small amounts. These features hint at weather processes operating on Mars that we've never observed directly. Subsurface interactions between ice, soil, and the thin atmosphere that create temporary conditions allowing liquid water to exist. The weather on Mars tells us the story of a world in transition, a planet that once had a much thicker atmosphere and possibly even liquid water flowing across its surface. The current weather patterns are the remnants of a more dynamic past, echoes of what Mars once was, and hints of what it might become as its atmosphere continues to slowly leak away into space. As we prepare to leave Mars behind and journey toward the outer solar system, we carry with us the image of a world where weather operates on truly planetary scales, where storms can engulf entire worlds, and where the dance between ice, dust, and thin atmosphere creates phenomena both familiar and utterly alien. Our next destination takes us across the asteroid belt and into the realm of the gas giants, where we'll encounter weather systems so massive and powerful they challenge our understanding of what's possible in planetary atmospheres. We're heading toward Jupiter, the king of planets, where storms larger than entire worlds have raged for centuries, and where the very concept of weather takes on meanings we never imagined. Jupiter looms before us like a cosmic artwork painted in bands of cream, brown, and orange. This giant world, more massive than all other planets in our solar system combined, is a laboratory of extreme weather, where storms dwarf continents and winds race at speeds that would tear apart any earthly weather system. The Great Red Spot dominates Jupiter's southern hemisphere, a storm so large that 3 Earths could fit comfortably inside its swirling embrace. This isn't just any storm. It's a weather system that has been raging continuously for at least 300 years, possibly much longer. Imagine a hurricane that began before the American Revolution and is still spinning today, growing and shrinking but never disappearing, a testament to the incredible power of Jovian meteorology. This great storm rotates counterclockwise, an anticyclonic system that generates winds reaching 268 miles per hour at its edges. The distinctive red color that gives the Great Red Spot its name remains one of the mysteries of planetary science. Some theories suggest the color comes from complex organic compounds created by lightning and ultraviolet radiation, while others propose it results from sulfur compounds dredged up from deeper layers of Jupiter's atmosphere. But the Great Red Spot is just the most famous of Jupiter's weather phenomena. The entire planet is wrapped in bands of swirling clouds that create Jupiter's characteristic striped appearance. These bands aren't just visual features, they're massive jet streams of ammonia and water vapor that circle the entire planet. The light-colored bands, called zones, are regions of upwelling where warm gases rise from Jupiter's interior. The darker bands, called belts, are areas where cooler gases sink back down into the planet's depths. These jet streams race around Jupiter at incredible speeds, some reaching 360 miles per hour. Unlike Earth's jet streams, which are relatively narrow ribbons of fast-moving air, Jupiter's atmospheric bands are thousands of miles wide and extend deep into the planet's atmosphere. They're powered not primarily by solar heating, as weather systems are on Earth, but by heat flowing up from Jupiter's interior. Jupiter generates more heat than it receives from the Sun, radiating about 2.5 times more energy than it absorbs from solar radiation. This internal heat source, left over from the planet's formation 4.5 billion years ago, drives weather patterns unlike anything in the inner solar system. The combination of rapid rotation, massive size, and internal heat creates a meteorological engine of almost unimaginable power. Recent observations from spacecraft have revealed that Jupiter's weather extends far deeper than anyone expected. The colorful bands and swirling storms we see from space are just the surface expression of weather systems that penetrate thousands of miles into the planet's interior. The Great Red Spot, for instance, appears to have roots extending more than 200 miles down into Jupiter's atmosphere. At Jupiter's poles, spacecraft have discovered something that defied all expectations. Instead of the simple polar weather patterns scientists anticipated, they found massive cyclonic storms arranged in geometric patterns. At the North Pole, 8 cyclones surround a central storm, each one larger than the biggest hurricanes on Earth, arranged in a nearly perfect octagonal pattern. The South Pole displays 5 cyclones arranged around a central storm in a pentagonal formation. These polar cyclones are each several thousand miles across and have been remarkably stable since their discovery. They represent a form of atmospheric organization that exists nowhere else in our solar system, a type of weather pattern that challenges our understanding of how planetary atmospheres can organize themselves. Lightning on Jupiter is another marvel that showcases the planet's extreme weather. Jovian lightning bolts are 3 times more powerful than the strongest lightning on Earth, crackling through clouds of ammonia and creating electromagnetic disturbances that can be detected by radio telescopes across the solar system. These lightning storms can persist for months, illuminating the planet's cloud tops with flashes visible from space. The clouds themselves are composed of materials that would be toxic to Earth life. Ammonia ice crystals float in the upper atmosphere, while deeper clouds may contain water vapor and more exotic compounds. The different cloud compositions create the varied colors we see in Jupiter's atmospheric bands, from the pale yellows and whites of ammonia clouds to the deeper browns and reds of more complex chemical compounds. Jupiter's weather also influences its many moons, particularly the 4 large Galilean satellites. The planet's powerful magnetic field, fed by electrical currents in its metallic hydrogen core, interacts with the thin atmospheres of moons like Io and Europa, creating auroras and atmospheric phenomena on these distant worlds. As we observe Jupiter's magnificent weather systems, we're witnessing atmospheric processes operating on scales that humble any earthly comparison. This is weather as a cosmic force, storms that persist for centuries, winds that could circle our entire planet in hours, and atmospheric dynamics powered by the fundamental heat of planetary formation itself. Jupiter shows us that weather isn't limited to the thin atmospheric shells surrounding rocky planets like Earth and Mars. In the realm of gas giants, entire worlds become weather systems, where the boundary between planet and atmosphere disappears, and where meteorology operates according to rules written by gravity, rotation, and the primordial heat of cosmic creation. As we drift away from Jupiter's mesmerizing storms, our cosmic journey carries us deeper into the outer solar system, where we encounter a world that defies imagination, with weather patterns so alien they seem crafted by some cosmic artist with an otherworldly sense of geometry. Saturn appears before us like a celestial jewel, its famous rings catching and reflecting sunlight in ways that make the entire system glow with ethereal beauty. But beyond those magnificent rings lies an atmosphere that harbors some of the most mysterious weather phenomena in our solar system. Here, nearly 1 billion miles from the Sun, where sunlight is 100 times weaker than what we receive on Earth, weather systems rage with a fury that makes earthly hurricanes seem gentle by comparison. The first thing that strikes you about Saturn's weather is the sheer violence of its winds. While Jupiter impressed us with its great red spot and banded atmosphere, Saturn takes atmospheric fury to an entirely different level. Winds scream across this ringed world at speeds exceeding 1,600 miles per hour, making Saturn's atmosphere the windiest place in our solar system after Neptune. These supersonic winds carve Saturn's atmosphere into alternating bands of gold, brown, and cream, similar to Jupiter's stripes but with their own unique character. The planet's rapid rotation, completing a full day in just over 10 hours, creates a centrifugal force so powerful it actually distorts Saturn's shape, making it noticeably flattened at the poles. This spinning motion feeds energy into the atmospheric jet streams, accelerating them to velocities that would instantly destroy any aircraft ever built by human hands. But Saturn's most enigmatic weather feature exists at its North Pole, where nature has created something so geometrically perfect it seems almost artificial. There, spanning 20,000 miles across, is a hexagonal jet stream, a 6-sided atmospheric pattern that has puzzled scientists since its discovery. This isn't just a vague hexagonal shape in the clouds. It's a precisely geometric formation with straight edges and sharp corners, as if someone took a cosmic ruler and drew a perfect hexagon in Saturn's atmosphere. The hexagon rotates as a solid structure, completing one rotation every 10 hours and 39 minutes, exactly matching Saturn's internal rotation period. This suggests that the hexagon is somehow connected to the planet's deep interior, a manifestation of forces operating far beneath the visible cloud layers. The jet stream that forms the hexagon's edges maintains winds of about 200 miles per hour, fast enough to circle Earth's equator in less than 5 days. At the center of this hexagonal marvel sits a massive vortex, a cyclonic storm that marks Saturn's north pole. This polar storm is larger than Earth and has been observed to change color over time, shifting from blue to gold and back again as different atmospheric chemicals rise and fall within its swirling depths. The eye of this storm is remarkably well defined, creating a structure that resembles a cosmic hurricane frozen in geometric perfection. What makes the hexagon even more mysterious is that nothing like it exists anywhere else in the solar system. Scientists have created similar hexagonal patterns in laboratory experiments involving rotating fluids, but scaling these effects up to planetary dimensions requires atmospheric dynamics that we're still struggling to understand. The hexagon represents a form of atmospheric self-organization that challenges our basic understanding of how weather systems can maintain such geometric precision across such vast scales. Saturn's weather extends far beyond this polar curiosity. Every few decades, the planet experiences what astronomers call the Great White Spot, a massive storm system that can grow to encompass areas larger than Earth's entire surface. Unlike Jupiter's Great Red Spot, which persists for centuries, Saturn's Great White Spots appear roughly every 30 Earth years, coinciding with Saturn's summer solstice in the northern hemisphere. These periodic storms begin as small disturbances deep within Saturn's atmosphere, but they can rapidly expand into planet-girdling tempests that completely encircle the globe. The storms appear brilliant white because they dredge up ammonia ice from deeper atmospheric layers, creating bright plumes that contrast sharply with the planet's normal golden hues. These storms can persist for months, gradually spreading around Saturn's entire circumference before finally dissipating. The most recent Great White Spot, observed in detail by the Cassini spacecraft, revealed the incredible power of Saturnian meteorology. The storm generated lightning bolts 10,000 times more powerful than typical Earth lightning, creating electromagnetic disturbances that could be detected from millions of miles away. The storm's head, where the most intense activity occurred, measured over 6,000 miles across and featured updrafts so powerful they punched through multiple layers of Saturn's atmosphere. Saturn's extreme distance from the Sun means that its weather operates on different principles than the inner planets. With surface temperatures averaging negative 285 degrees Fahrenheit, water would be frozen solid, so Saturn's clouds are composed of ammonia ice and other exotic compounds that remain volatile at these frigid temperatures. The planet's internal heat source, like Jupiter's, plays a crucial role in driving atmospheric circulation. But Saturn radiates even more excess heat relative to what it receives from the Sun. The interplay between Saturn's rings and its atmosphere creates unique weather phenomena found nowhere else. The rings cast shadows on the planet's cloud tops, creating temperature variations that influence wind patterns and storm formation. During Saturn's equinoxes, when the rings edge on to the Sun, these shadow effects become particularly pronounced, creating spoke-like patterns in the atmospheric circulation. Lightning on Saturn tells its own fascinating story of atmospheric chemistry and dynamics. The lightning is primarily detected in radio wavelengths, creating what astronomers call Saturn electrostatic discharges, or SEDS. These electrical storms can last for months, far longer than any thunderstorm on Earth, suggesting that Saturn's atmospheric dynamics operate on timescales that dwarf terrestrial weather patterns. The chemical composition of Saturn's atmosphere creates weather phenomena that would be utterly alien to earthly experience. Clouds of ammonia ice drift through an atmosphere composed primarily of hydrogen and helium, occasionally punctuated by deeper layers containing water vapor and complex hydrocarbon compounds. The interaction between these different chemical layers creates the varied colors and textures we observe in Saturn's cloud bands. Saturn's numerous moons also influence its atmospheric dynamics in subtle but important ways. The gravitational tugs of moons like Titan and Enceladus create tidal effects in Saturn's atmosphere, contributing to the complex patterns of circulation that shape the planet's weather systems. Some scientists theorize that the regular appearance of the Great White Spot might be influenced by the orbital periods of Saturn's major moons, though this connection remains speculative. As we continue our journey through Saturn's neighborhood, we're struck by how this ringed giant demonstrates that weather can take forms limited only by the laws of physics themselves. The hexagonal storm, the great white spots, the supersonic winds, all of these phenomena remind us that nature's creativity extends far beyond our earthbound experience. Saturn's weather operates according to principles that stretch our understanding and challenge us to think about atmospheric dynamics in entirely new ways. From Saturn's geometric storms to the ice giants that await us in the outer darkness, our solar system continues to reveal weather patterns that expand our definition of what's possible when gravity, rotation, and atmospheric chemistry combine on planetary scales. Each world we visit teaches us something new about the infinite variety of ways that matter and energy can organize themselves into the phenomena we call weather. Our journey now takes us beyond the familiar realm of the gas giants, into the mysterious domain of the ice giants, where we'll encounter weather systems operating under conditions so extreme, they challenge everything we thought we knew about planetary atmospheres. We're approaching Uranus, a world that rolls through space on its side, creating seasons and weather patterns unlike anything else in our solar system. Uranus presents itself to us as a serene, blue-green disk, deceptively peaceful in appearance. This distant world, nearly 2 billion miles from the Sun, receives only 1/400th the amount of sunlight that warms our Earth. Yet beneath that tranquil exterior lies an atmosphere capable of producing some of the most extreme weather phenomena we've yet encountered. The most striking thing about Uranus is its bizarre orientation. While all other planets spin roughly upright as they orbit the Sun, Uranus rotates on its side, tilted at nearly 90 degrees from vertical. This dramatic tilt creates seasons unlike anywhere else in our solar system. For 42 Earth years, one hemisphere of Uranus experiences continuous sunlight, while the other endures endless winter darkness. Then, as the planet continues its 84-year orbit, the seasons reverse, plunging the previously sunlit hemisphere into decades of darkness. This extreme seasonal variation creates weather patterns that unfold over timescales that challenge human comprehension. Imagine summer lasting longer than a human lifetime, followed by an equally lengthy winter where the sun never rises above the horizon. These epic seasons drive atmospheric dynamics that we're only beginning to understand, creating weather systems that evolve and change over periods measured in decades rather than days or weeks. When the Voyager spacecraft first flew past Uranus in 1986, the planet appeared almost featureless, earning it a reputation as the most boring world in the outer solar system. But this apparent tranquility was misleading. Uranus happened to be near its solstice when Voyager arrived, with one hemisphere in continuous sunlight and the other in perpetual darkness. The lack of temperature contrast between day and night sides created relatively calm atmospheric conditions, but as Uranus has continued along its orbital path and approached its equinox, the planet has revealed its hidden meteorological fury. Modern telescopes have detected wind speeds reaching 560 miles per hour, fast enough to circumnavigate Earth in less than 2 days. These winds blow through an atmosphere so cold that temperatures drop to negative 320 degrees Fahrenheit, cold enough to freeze nitrogen solid. The most dramatic change in Uranian weather occurred during the early 2000s, when the planet began developing massive storm systems that transformed its appearance. Enormous white clouds appeared in the planet's atmosphere, some spanning areas larger than North America. These storms produced the fastest winds ever recorded on Uranus, with gusts reaching 824 miles per hour, velocities that would instantly vaporize any earthly structure. These sudden weather changes coincided with Uranus approaching its equinox, when both hemispheres began receiving equal amounts of sunlight for the first time in decades. The resulting temperature contrasts apparently triggered atmospheric instability that had been building up during the long seasonal transition. Scientists observed what they described as 4th of July fireworks in the Uranian atmosphere, brilliant storms that flared up with spectacular intensity before gradually fading away. The composition of Uranus's atmosphere creates unique weather phenomena found nowhere else in our solar system. Unlike the hydrogen and helium atmospheres of Jupiter and Saturn, Uranus contains significant amounts of water, methane, and ammonia ices. These materials give the planet its distinctive blue-green color, as atmospheric methane absorbs red light while allowing blue and green wavelengths to scatter back into space. The presence of these ices creates clouds that exist at multiple levels throughout the atmosphere. High-altitude clouds of methane ice crystals create wispy formations that can cast shadows on lower cloud decks 35 miles below. Deeper in the atmosphere, clouds of ammonia and hydrogen sulfide create darker bands that give structure to the planet's otherwise uniform appearance. Uranus radiates almost no excess heat compared to the energy it receives from the Sun, unlike Jupiter and Saturn, which are powered by internal heat sources. This means that Uranian weather is driven almost entirely by the weak solar energy that reaches this distant world, supplemented by the dramatic seasonal variations created by the planet's tilted axis. The lack of internal heat makes Uranus's atmosphere remarkably stable most of the time, but also creates the potential for sudden, dramatic changes when conditions finally do shift. The magnetic field of Uranus adds another layer of complexity to its atmospheric dynamics. The planet's magnetic field is tilted 60 degrees from its rotational axis and offset from the planet's center, creating a twisted, irregular magnetosphere that affects how the solar wind interacts with the upper atmosphere. This unusual magnetic geometry may contribute to the planet's sporadic auroral activity and influence the formation of high-altitude clouds. Recent observations have revealed that Uranus experiences seasonal changes in its cloud formation patterns that mirror the planet's extreme axial tilt. As different hemispheres receive varying amounts of sunlight throughout the 84-year orbital period, cloud activity shifts from one pole to the other in a slow, majestic dance that unfolds over decades. The atmosphere of Uranus also exhibits unique chemical weather patterns. Photochemical reactions driven by ultraviolet light from the sun create complex hydrocarbon compounds in the upper atmosphere. These reactions vary with the seasons, producing different chemical hazes and cloud compositions as the amount and angle of sunlight changes throughout the Uranian year. As we prepare to leave Uranus behind and venture toward the final planet of our journey, we carry with us the image of a world where weather operates on the longest timescales in our solar system. Uranus teaches us that atmospheric dynamics can unfold over periods that span multiple human generations, creating weather patterns that challenge our Earth-centered notions of meteorological time. The extreme seasons of Uranus remind us that weather is ultimately about energy distribution and temperature contrasts, and that these fundamental principles can create phenomena far removed from our everyday experience. From the decades-long seasons to the sudden explosive storms, Uranian weather demonstrates that even the most apparently tranquil worlds can harbor meteorological surprises that expand our understanding of what's possible in planetary atmospheres. Our final destination awaits us at the very edge of the solar system, where we'll encounter the windiest world of all, a deep blue realm where storms rage with supersonic fury across an atmosphere colder than liquid nitrogen. We're approaching Neptune, the most distant giant planet, where weather reaches its most extreme expression in our cosmic neighborhood. Neptune emerges from the cosmic darkness like a sapphire jewel suspended in the vast emptiness, its deep azure surface concealing the most violent weather in our entire solar system. Here, at the outermost reaches of the planetary realm, nearly 3 billion miles from the Sun's warming embrace, we encounter a world where the very concept of extreme weather reaches its ultimate expression. As we approach this distant ice giant, the first thing that strikes us is the profound isolation of this realm. Sunlight here is 900 times weaker than what bathes our Earth, so faint that noon on Neptune would seem like deep twilight to human eyes. The Sun appears as nothing more than a bright star in Neptune's sky, providing barely enough energy to warm a snowflake. Yet despite this incredible distance from our solar system's furnace, Neptune produces weather systems of such staggering violence they dwarf the fury of any earthly storm. Neptune holds the record as the windiest world in our solar system, with atmospheric currents that race through the planet's hydrogen and helium atmosphere at speeds exceeding 1,300 miles per hour. These are not gentle breezes or even powerful gusts. These are supersonic winds that move at velocities 3 times faster than the strongest hurricanes on Earth, 9 times faster than the winds that topple trees and level buildings in our most severe storms. What makes these incredible wind speeds even more mysterious is that Neptune receives so little energy from the Sun. On Earth, our weather systems are driven by solar heating that creates temperature differences between the equator and poles, between day and night. But Neptune's weather operates according to different rules entirely. The planet radiates 2.5 times more energy than it receives from the distant Sun, suggesting that its meteorological fury is powered by heat flowing up from the planet's interior, energy left over from the world's formation 4.5 billion years ago. This internal heat source creates atmospheric dynamics, unlike anything we've encountered in our journey through the solar system. The combination of rapid rotation, internal heating, and the unique chemistry of Neptune's atmosphere generates weather patterns that seem to violate our understanding of how planetary meteorology should work. It's as if Neptune has discovered some secret of atmospheric physics that allows it to maintain incredibly violent weather systems despite existing in the cold depths of interplanetary space. The most famous feature of Neptunian weather was discovered when Voyager 2 flew past the planet in 1989. The spacecraft revealed a massive dark storm system that astronomers dubbed the Great Dark Spot, an anticyclonic tempest comparable in size to Jupiter's Great Red Spot. This enormous weather system was roughly the size of Earth, a swirling vortex of darkness that appeared to be a window into deeper layers of Neptune's atmosphere. But unlike Jupiter's Great Red Spot, which has persisted for centuries, Neptune's Great Dark Spot demonstrated the dynamic and changeable nature of weather on this distant world. When the Hubble Space Telescope turned its gaze toward Neptune just a few years later, the Great Dark Spot had completely vanished, disappearing as mysteriously as it had formed. In its place, new storm systems had appeared, including another dark vortex near the planet's north pole, accompanied by bright clouds of methane ice crystals. This rapid appearance and disappearance of major storm systems reveals something profound about Neptune's atmospheric dynamics. The planet's weather operates on timescales that are both faster and more dramatic than the relatively stable systems we observe on Jupiter and Saturn. Neptune's storms can form, rage with incredible intensity, and then dissipate within periods measured in years rather than centuries, creating an ever-changing atmospheric landscape that challenges our ability to predict or understand its behavior. The dark appearance of Neptune's major storms creates one of the most striking visual phenomena in planetary meteorology. These storms appear dark not because they're composed of dark materials, but because they're essentially atmospheric holes that allow us to peer deeper into Neptune's atmosphere. Like looking down into the eye of a hurricane from space, these dark spots reveal lower atmospheric layers that are normally hidden beneath higher cloud decks. Surrounding these dark vortices are some of the most beautiful cloud formations in the solar system. Bright white clouds of methane ice crystals stream away from the storm systems like cosmic contrails, stretched into elegant streamers by the planet's fierce winds. These cirrus-like formations can extend for thousands of miles, creating delicate patterns that contrast dramatically with the violent storms that spawn them. The methane in Neptune's atmosphere plays a crucial role in creating the planet's distinctive deep blue color and its unique weather patterns. Methane absorbs red light while allowing blue wavelengths to be scattered back into space, giving Neptune its characteristic sapphire hue. But methane also condenses into ice crystals in the planet's cold upper atmosphere, creating clouds that exist at multiple altitudes throughout the atmospheric column. At the highest levels, wispy cirrus clouds of methane ice drift through the thin upper atmosphere, casting shadows on cloud decks dozens of miles below. Deeper in the atmosphere, scientists believe clouds of hydrogen sulfide and ammonia exist at higher pressures, while even deeper layers may contain clouds of water ice and other compounds. This multi-layered cloud structure creates the complex interplay of light and shadow that gives Neptune's storms their dramatic appearance. The seasonal variations on Neptune unfold over periods that challenge human comprehension. Each season on this distant world lasts for approximately 40 years, meaning that summer in Neptune's southern hemisphere began around 1985 and will continue until sometime in the 2020s. These decades-long seasons create gradual changes in atmospheric circulation patterns that we're only beginning to observe and understand. Recent observations have revealed that Neptune's atmospheric activity varies with these long seasonal cycles. As different hemispheres receive varying amounts of the sun's weak energy, cloud formation patterns shift and change, creating weather variations that unfold over timescales longer than most human careers. The planet's south pole has been gradually warming over the past few decades, a process that may be influencing the formation and behavior of the massive storm systems we observe. Lightning on Neptune creates electromagnetic phenomena that can be detected by radio telescopes across the solar system, though the exact nature of these electrical discharges remains mysterious. The combination of the planet's powerful magnetic field and its violent atmospheric dynamics creates conditions for electrical activity unlike anything found elsewhere in our solar system. The interaction between Neptune's weather and its system of moons adds another layer of complexity to this distant world's meteorology. The planet's largest moon, Triton, orbits in a retrograde direction and possesses its own thin atmosphere and weather patterns, including nitrogen geysers that shoot material several miles into space. The gravitational influence of Triton and Neptune's other moons creates subtle tidal effects in the planet's atmosphere that may influence the formation and evolution of its storm systems. Perhaps the most humbling aspect of Neptune's weather is how it demonstrates the incredible power of planetary atmospheric systems operating under conditions we can barely imagine. Here is a world where temperatures never rise above -360 degrees Fahrenheit, where the atmosphere is so cold that methane freezes solid, yet where winds rage with velocities that would instantly destroy any structure humans have ever built. Neptune's weather reminds us that atmospheric dynamics operate according to fundamental physical principles that can create phenomena far beyond our everyday experience. The planet's supersonic winds, its rapidly changing storm systems, and its beautiful methane clouds all emerge from the same basic processes that drive weather on Earth, but operating under conditions so extreme they produce results that seem almost magical. As we observe Neptune's magnificent and terrible weather systems, we're witnessing the outer limits of what's possible in planetary meteorology within our solar system. This deep blue world, spinning in the cosmic cold at the very edge of the sun's domain, shows us that weather can exist and thrive even in the most seemingly hostile environments, powered by forces that reach back to the very formation of the planets themselves. The winds of Neptune carry with them the story of planetary formation, the gradual cooling of a world born in fire and ice, and the incredible persistence of atmospheric dynamics across billions of years. Every supersonic gust, every swirling storm, every delicate methane cloud represents the ongoing expression of forces that have been shaping this world since the solar system itself was young. As our cosmic journey through the weather systems of the solar system draws toward a close, Neptune serves as a fitting finale to our exploration of planetary meteorology. From Mercury's temperature extremes to Neptune's supersonic winds, from Venus's acid rain to Jupiter's centuries-old storms, we've witnessed weather phenomena that expand our understanding of what's possible when matter and energy interact on planetary scales. Each world we've visited has taught us something unique about the incredible diversity of atmospheric processes that exist beyond our Earth. We've seen weather systems powered by everything from direct solar heating to internal planetary heat, from rapid rotation to extreme seasonal variations. We've observed storms that persist for centuries and others that appear and disappear within years, winds that barely stir the surface and others that race at supersonic speeds. The weather systems of our solar system remind us that Earth's gentle climate, with its moderate temperatures and life-sustaining precipitation, represents something precious and rare in the cosmic context. Our world exists in a narrow zone of conditions that allow liquid water to exist, and weather systems to operate within bounds that life can not only tolerate, but actually depend upon for survival. Yet the alien weather patterns we've explored also demonstrate the incredible creativity of natural processes operating under different conditions. The hexagonal storm at Saturn's pole, the great red spot of Jupiter, the planet-wide dust storms of Mars. Each of these phenomena reveals new possibilities for how atmospheric systems can organize themselves and persist across vast scales of space and time. The sulfuric acid rain of Venus warns us about the potential consequences of runaway greenhouse effects, while the thin atmosphere of Mars shows us a world where weather operates according to principles quite different from our earthbound experience. The gas giants reveal weather as a cosmic force operating on scales that humble any earthly comparison, while the ice giants demonstrate that even in the cold depths of the outer solar system, atmospheric dynamics can create phenomena of stunning beauty and terrible power. As you drift towards sleep tonight, carried along by the gentle rhythm of your own breathing, remember that you exist within your own perfect atmospheric cocoon, surrounded by weather systems that nurture rather than destroy, that create conditions for incredible diversity rather than hostile wastelands. The air that fills your lungs, the clouds that drift across your sky, the gentle rain that waters the earth, all of these represent something miraculous when viewed against the backdrop of the extreme weather systems that dominate every other world in our solar system. Our cosmic journey through the weather of the planets reveals not just the incredible diversity of atmospheric phenomena that exist beyond Earth, but also the preciousness of our own world's perfect balance. In understanding the alien weather patterns of distant worlds, we gain a deeper appreciation for the gentle, life-sustaining climate that makes our blue marble home such a rare and wonderful place in the vast cosmos. The storms of Jupiter may rage for centuries, the winds of Neptune may scream at supersonic speeds, and the acid clouds of Venus may create hellish conditions beyond imagination. But here on Earth, weather serves as the sculptor of landscapes, the distributor of water, and the creator of the very conditions that allow consciousness to emerge and contemplate its place in the universe. Tonight, as you rest beneath Earth's protective atmospheric blanket, you can dream of alien storms and distant weather systems, knowing that you are safely cradled by the most perfect weather system in the known universe, where every breeze and every raindrop participates in the grand dance that makes life possible in an otherwise hostile cosmos. Our cosmic weather journey has taken us to the very edge of the planetary realm, But there's one more chapter to our story that reveals perhaps the most profound truth about weather in our solar system. As we drift back toward the inner worlds, let's pause for a moment and consider the invisible threads that connect all these diverse atmospheric phenomena. The fundamental forces that shape weather across the entire cosmic neighborhood we call home. From our vantage point between the worlds, we can see how each planet's weather tells a unique story about the delicate balance between energy, matter, and time. The scorching days and frozen nights of Mercury remind us that weather doesn't always require thick atmospheres or complex chemistry. Sometimes, the most dramatic meteorological events emerge from the simplest interactions between solar radiation and bare rock, creating temperature swings more extreme than any earthly storm. Venus teaches us about the terrifying power of atmospheric chemistry gone wrong, where greenhouse gases can transform a world into a hellscape of molten temperatures and acid rain. The beautiful white clouds that make Venus shine like a beacon in our evening sky hide a cautionary tale about what happens when atmospheric composition tips beyond a critical threshold, creating weather so hostile it challenges our understanding of planetary habitability. Mars shows us weather as a force of planetary change, where massive dust storms redistribute the very surface of a world, and where the thin atmosphere creates meteorological phenomena that exist nowhere else. The seasonal advance and retreat of the Martian polar ice caps, the formation of clouds over ancient volcanic peaks, the mysterious dark streaks that appear and disappear on hillsides during warm seasons, all of these reveal weather as an active participant in planetary evolution. The gas giants have shown us weather as a cosmic force operating on scales that dwarf earthly comprehension. Jupiter's Great Red Spot demonstrates how atmospheric systems can achieve a kind of immortality, persisting for centuries while smaller storms are born, rage briefly, and disappear into the swirling chaos of the giant planet's atmosphere. The hexagonal storm at Saturn's pole reveals that weather can organize itself into geometric patterns of stunning precision, creating atmospheric art on a planetary canvas. The ice giants in the outer solar system have taught us that weather doesn't require warmth or familiar conditions to create phenomena of incredible beauty and power. Uranus, with its decades-long seasons and sudden explosive storms, shows us meteorology operating on timescales that challenge human understanding. Neptune, with its supersonic winds racing through an atmosphere colder than liquid nitrogen, demonstrates that the most extreme weather in our solar system exists in the coldest, most distant realms. But perhaps the most remarkable revelation of our journey is how all of these diverse weather systems emerge from the same fundamental physical principles: gravity, rotation, heating, cooling, pressure differences, chemical reactions. All of these basic forces combine in different ways on different worlds to create the incredible variety of atmospheric phenomena we've witnessed. The temperature gradients that drive Earth's gentle trade, winds operate according to the same principles that power Jupiter's centuries-old storms and Neptune's supersonic atmospheric currents. The seasonal changes that bring spring flowers and autumn leaves to our world are governed by the same orbital mechanics that create Uranus's 40-year seasons and Mars's planet-spanning dust storms. This universality of physical law means that weather, in all its myriad forms throughout the solar system, represents variations on common themes: heat seeking equilibrium, matter responding to pressure differences, rotation creating patterns of circulation, chemistry transforming simple compounds into complex atmospheric phenomena. These processes operate everywhere, but the specific conditions on each world, the atmospheric composition, the distance from the Sun, the rate of rotation, the presence or absence of magnetic fields, all of these factors combine to create the unique meteorological fingerprint of each planet. Consider how the presence of liquid water has shaped Earth's weather into something uniquely nurturing for life. Water's ability to exist as solid, liquid, and gas at Earth's temperatures and pressures creates weather systems based on evaporation, condensation, and precipitation. This water cycle moderates temperatures, distributes energy around the planet, and creates the stable conditions that have allowed life to flourish for billions of years. On other worlds, different substances play similar roles. The ammonia clouds of Jupiter and Saturn, the methane hazes of Titan, the carbon dioxide cycles that drive Martian seasonal changes. All of these represent variations on the theme of phase transitions creating weather. Each world uses the materials available to it, combined with its unique environmental conditions, to create atmospheric systems that are both alien and familiar. The magnetic fields that surround many planets add another layer of complexity to interplanetary weather. These invisible shields, generated by electrical currents deep within planetary cores, interact with the solar wind to create phenomena that blur the line between weather and space physics. The auroras that dance through Earth's polar skies are cousins to the plasma tornadoes that spiral down to Mercury's surface and the radio emissions generated by Jupiter's powerful magnetosphere. Even the solar wind itself can be thought of as a kind of weather, the Sun's own atmosphere extending throughout the solar system and influencing atmospheric conditions on every world it touches. Solar storms and coronal mass ejections create space weather that can affect planetary magnetospheres, alter atmospheric chemistry, and influence the formation of clouds and storms on worlds billions of miles away. This interconnectedness reveals something profound about our solar system. We often think of planets as isolated worlds, each with its own separate weather systems operating independently. But the reality is far more complex and beautiful. Our solar system is a single, integrated system, where the weather on one world can influence conditions on others through the medium of the solar wind, gravitational interactions, and the exchange of matter between planetary atmospheres. The dust kicked up by Martian storms doesn't just stay on Mars. Some of it escapes into interplanetary space, carried by the solar wind to other worlds. The water vapor in Earth's upper atmosphere can escape to space and potentially reach other planets. The complex organic molecules created in Titan's atmosphere by solar radiation and cosmic rays represent a form of atmospheric chemistry that might seed other worlds with the building blocks of more complex weather systems. As we contemplate these vast scales of interaction and influence, we begin to see weather not just as local atmospheric phenomena, but as expressions of cosmic processes that operate throughout the universe. The same physical principles that govern weather in our solar system apply to the atmospheres of planets orbiting other stars, to the vast gas clouds that drift between the stars, to the accretion disks that spiral around black holes. Weather, we realize, is one of the fundamental ways that matter and energy organize themselves in the universe. From the gentle circulation patterns in a teacup of cooling coffee to the massive cyclonic storms that rage in the atmospheres of gas giant planets, from the thermal currents that rise from sun-warmed pavement to the jet streams that circle entire worlds. All of these phenomena represent the same basic physical processes operating at different scales. This perspective transforms our understanding of Earth's weather from something local and familiar into something cosmic and profound. Every cloud that drifts across our sky, every breeze that stirs the leaves, every raindrop that falls to nourish the soil, participates in processes that connect our world to the larger patterns of matter and energy that shape the entire universe. The gentle weather systems that make Earth a haven for life emerge from the same forces that create the hellish conditions on Venus, the frozen wastelands of the outer moons, and the supersonic winds of Neptune. What makes Earth special is not that it operates according to different physical laws, but that the specific combination of conditions here, the distance from the sun, the composition of the atmosphere, the presence of liquid water, the strength of the magnetic field, all of these factors have combined to create weather systems that nurture complexity rather than destroy it. This realization fills our earthly weather with new meaning and wonder. When you feel the warmth of sunlight on your face, you're experiencing the same stellar radiation that drives the extreme temperature variations on Mercury and powers the massive storm systems of the gas giants. When you watch clouds form and dissipate in Earth's sky, you're witnessing phase transitions similar to those that create the methane hazes of Titan and the sulfuric acid clouds of Venus. The water that falls as gentle rain in Earth's temperate regions participates in the same fundamental process of condensation and precipitation that creates the snow observed falling through Mars's thin atmosphere and the exotic precipitation that may occur in the upper layers of gas giant atmospheres. Every weather phenomenon on Earth connects us to the larger community of worlds that share our solar system and reminds us that we are participants in cosmic processes that extend far beyond our planetary boundaries. As you settle into the quiet moments before sleep, surrounded by the gentle embrace of Earth's nurturing atmosphere, you can let your mind drift among these cosmic weather systems. You can imagine the sulfuric acid rain that never reaches Venus's molten surface, the centuries-old storms that rage in Jupiter's colorful bands, the hexagonal perfection of Saturn's polar tempest, the supersonic winds that scream through Neptune's frozen atmosphere. But you can also appreciate the miraculous balance that creates Earth's perfect climate, where weather serves life rather than destroying it, where atmospheric systems operate within the narrow range of conditions that allow water to flow, plants to grow, and consciousness to emerge and contemplate its place in the cosmic dance of matter and energy. The weather outside your window tonight, whether it's clear and starlit or cloudy and calm, represents something precious and rare when viewed against the backdrop of the extreme atmospheric conditions that dominate every other world we've visited. Earth's weather is not just meteorology, it's the foundation of everything we know and love about our world, the invisible sculptor that shapes landscapes, distributes life-giving water, and creates the very conditions that make our existence possible. In understanding the alien weather systems of distant worlds, we gain a deeper appreciation for the perfect balance that makes Earth such a remarkable oasis in the cosmic desert. Our journey through the solar system's weather has shown us both the incredible diversity of atmospheric phenomena and the fundamental unity of the physical processes that create them all. Tonight, as you rest beneath Earth's protective atmospheric blanket, you are cradled by weather systems that represent the culmination of billions of years of planetary evolution, a delicate balance of forces that has created the most hospitable climate in the known universe. Sweet dreams, fellow traveler in this cosmic weather system we call home. Cosmic weather system we call home. Our cosmic journey through the weather of the planets has revealed the incredible diversity of atmospheric phenomena that exist beyond our familiar blue world. But as we drift back toward Earth through the starlit darkness, there's one more profound truth about weather that connects every world we've visited, from Mercury's temperature extremes to Neptune's supersonic winds. You see, weather isn't just about wind and rain, heat and cold. It's about the fundamental dance between order and chaos that plays out across every atmospheric system in the universe. Each planet we've explored demonstrates this cosmic choreography in its own unique way, showing us how the same basic forces of nature can create phenomena ranging from gentle to utterly terrifying. Consider how energy flows through these distant worlds. On Mercury, the sun's raw power creates temperature swings so extreme they would instantly destroy any earthly weather system. Yet even in this harsh environment, patterns emerge. The rapid heating and cooling cycles create their own rhythm, a meteorological heartbeat that has pulsed steadily for billions of years. Venus shows us what happens when this energy dance spirals completely out of control. The greenhouse effect that makes Venus hotter than Mercury, despite being farther from the Sun, represents a cautionary tale written in atmospheric chemistry. Once the balance tipped beyond a critical point, Venus's weather became locked in a permanent state of hellish extremes, creating conditions so hostile they challenge our understanding of planetary habitability. Mars offers a different lesson about the relationship between energy and atmospheric dynamics. With its thin atmosphere and distant orbit, Mars receives only a fraction of the solar energy that drives Earth's weather systems. Yet this energy scarcity has created some of the most dramatic weather phenomena in our solar system. The massive dust storms that can engulf the entire planet demonstrate how even minimal energy inputs can create maximum atmospheric chaos when conditions align perfectly. The gas giants reveal weather as a cosmic force operating on scales that humble any earthly comparison. Jupiter's Great Red Spot has been raging for longer than human civilization has existed, powered not by solar energy, but by heat flowing up from the planet's interior. This ancient storm demonstrates how atmospheric systems can achieve a kind of immortality, persisting across centuries while smaller weather patterns are born, rage briefly, and disappear into the swirling chaos. Saturn's hexagonal storm system challenges our understanding of how atmospheric forces can organize themselves into geometric perfection. This six-sided tempest spanning 20,000 miles across represents a form of natural architecture that seems almost too precise to be real. Yet there it spins at Saturn's North Pole, a testament to the incredible organizing power of atmospheric dynamics operating at planetary scales. The ice giants in the outer solar system have shown us that weather doesn't require warmth or familiar conditions to create phenomena of stunning beauty and terrible power. Uranus, tilted on its side and experiencing seasons that last for decades, demonstrates how atmospheric systems can operate on timescales that challenge human comprehension. Neptune, with winds that race at supersonic speeds through an atmosphere colder than liquid nitrogen, shows us the most extreme weather in our solar system existing in the coldest, most distant realms. But perhaps the most remarkable aspect of our interplanetary weather journey is how it reveals the interconnectedness of all atmospheric systems. The same physical principles that govern Earth's gentle trade winds also power Jupiter's centuries-old storms and Neptune's supersonic atmospheric currents. The seasonal changes that bring spring flowers and autumn leaves to our world operate according to the same orbital mechanics that create Uranus's 40-year seasons and Mars's planet-spanning dust storms. This universality means that weather, in all its forms throughout the solar system, represents variations on common themes. Heat-seeking equilibrium, matter responding to pressure differences, rotation creating circulation patterns, chemistry transforming simple compounds into complex atmospheric phenomena. These processes operate everywhere, but the specific conditions on each world create unique meteorological fingerprints that tell the story of planetary formation and evolution. The presence of different atmospheric constituents on each world creates weather systems based on entirely different chemical cycles. Earth's water-based weather moderates temperatures and creates stable conditions perfect for life. Jupiter and Saturn use ammonia and hydrogen compounds to create their colorful banded atmospheres. The methane in Neptune's atmosphere creates its deep blue color and contributes to the formation of high-altitude ice crystal clouds that stream away from storm systems like cosmic contrails. Even the magnetic fields that surround many planets play crucial roles in shaping weather patterns. These invisible shields interact with the solar wind to create phenomena that blur the line between atmospheric science and space physics. The plasma tornadoes that spiral down to Mercury's surface, the auroras that dance through Earth's polar skies, and the radio emissions generated by Jupiter's powerful magnetosphere all represent different expressions of the same electromagnetic processes. The solar wind itself acts as a kind of interplanetary weather system, carrying the sun's influence to every corner of our solar system. Solar storms and coronal mass ejections create space weather that affects planetary atmospheres billions of miles away, altering atmospheric chemistry and influencing the formation of clouds and storms on distant worlds. This cosmic perspective reveals something profound about the nature of weather itself. What we experience as local atmospheric phenomena on Earth are actually expressions of universal processes that operate throughout the cosmos. The same forces that create gentle summer breezes in earthly gardens also generate the supersonic winds that rage through Neptune's frozen atmosphere and the centuries-old storms that swirl through Jupiter's colorful bands. Understanding this connection transforms our relationship with Earth's weather from something familiar and local into something cosmic and profound. Every cloud that drifts across our sky participates in processes that connect our world to the larger patterns of matter and energy that shape the entire universe. Every raindrop that falls to nourish the soil, every snowflake that dances in winter air, every gentle breeze that stirs the leaves, all of these phenomena link us to the vast community of worlds that share our solar system. But what makes Earth truly special among all the worlds we've visited isn't that our planet operates according to different physical laws. Rather, it's that the specific combination of conditions here has created weather systems that nurture complexity rather than destroy it. Our distance from the sun, the composition of our atmosphere, the presence of liquid water, the strength of our magnetic field, all of these factors have combined in perfect balance to create the most hospitable climate in the known universe. The gentle weather systems that make Earth a haven for life emerge from the same fundamental forces that create the hellish conditions on Venus, the frozen wastelands of the outer moons, and the supersonic winds of distant ice giants. What makes our world remarkable is not the absence of extreme weather, but the way our atmospheric systems operate within the narrow range of conditions that allow water to flow, plants to grow, and consciousness to emerge and contemplate its place in the cosmic dance. This realization fills earthly weather with new meaning and wonder. When you feel the warmth of sunlight on your skin, you're experiencing the same stellar radiation that creates Mercury's extreme temperature variations and powers the massive storm systems of the gas giants. When you watch clouds form and dissipate in our sky, you're witnessing phase transitions similar to those that create the methane hazes of distant moons and the sulfuric acid clouds of Venus. The water cycle that brings life-giving rain to Earth's continents operates according to the same principles of evaporation, condensation, and precipitation that create the exotic weather phenomena we observe on other worlds. The snow that falls in Earth's winter wonderlands participates in the same fundamental process that creates the carbon dioxide snow observed in Mars's thin atmosphere and the methane precipitation that may occur in the upper layers of gas giant atmospheres. Every weather phenomenon on Earth connects us to this larger community of worlds and reminds us that we are participants in cosmic processes that extend far beyond our planetary boundaries. The atmospheric systems that cradle our world in their gentle embrace are part of a vast network of weather patterns that extends throughout our solar system and beyond, connecting every planet, moon, and atmospheric system in an intricate web of physical relationships. As you prepare for sleep tonight, surrounded by the protective embrace of Earth's nurturing atmosphere, you can let your imagination drift among these cosmic weather systems. Picture the sulfuric acid rain that never reaches Venus's molten surface, the ancient storms that rage in Jupiter's colorful atmospheric bands, the geometric perfection of Saturn's hexagonal tempest, the supersonic winds that scream through Neptune's frigid atmosphere, but also take a moment to appreciate the miraculous balance that creates Earth's perfect climate, where weather serves life rather than destroying it, where atmospheric systems operate within precisely the right range of conditions to allow the incredible diversity of life that surrounds us. The gentle rain that waters our gardens, the seasonal changes that mark the passage of time, the moderate temperatures that make our world habitable, all of these represent something precious and rare when viewed against the backdrop of the extreme conditions that dominate every other world in our solar system. The weather outside your window tonight, whether it brings clear starlit skies or gentle clouds drifting through moonlight, represents the culmination of billions of years of planetary evolution. Earth's atmosphere is a delicate masterpiece of natural engineering, a complex system that has evolved over geological time to create the most hospitable environment in the known universe. In understanding the alien weather systems of distant worlds, we gain a deeper appreciation for the perfect balance that makes our blue marble such a remarkable oasis in the cosmic wilderness. Our journey through the solar system's diverse atmospheric phenomena has revealed both the incredible variety of weather patterns that exist beyond Earth and the fundamental unity of the physical processes that create them all. Tonight, as you rest beneath Earth's protective atmospheric blanket, you are cradled by weather systems that represent something truly miraculous in the context of our cosmic neighborhood. The air you breathe, the moderate temperatures that keep you comfortable, the water cycle that sustains all life on our planet. These are not just local conveniences, but cosmic rarities that make Earth the most precious world we know. Sweet dreams, fellow traveler. through this solar system of infinite atmospheric wonders. May your rest be as peaceful as a gentle summer evening, as refreshing as morning rain, and as nurturing as the perfect balance of forces that makes weather on Earth the foundation of everything we know and love about our extraordinary home in the vast cosmos. As our cosmic journey draws toward its gentle conclusion, we find ourselves contemplating something even more profound than the individual weather systems we've witnessed. Each world we've visited has shown us a different face of the same universal principles, like instruments in a vast cosmic orchestra, each playing its own unique melody while contributing to a grand symphony of atmospheric dynamics that spans the entire solar system. The patterns we've observed reveal themselves as expressions of something deeper, something that connects the microscopic dance of molecules in Earth's gentle breezes to the planet-spanning tempests that rage across Jupiter's ancient face. Every atmospheric phenomenon, from the simplest thermal current rising from sun-warmed ground to the most complex storm system swirling through alien skies, emerges from the same fundamental choreography between matter, energy, and time. Consider how rotation shapes weather across every world we've encountered. Mercury's slow, deliberate spin creates the extreme day-night temperature cycles that define its harsh meteorology. Earth's 24-hour rotation generates the Coriolis effect that curves our hurricanes into their characteristic spiral patterns and drives the jet streams that circle our planet. Mars experiences dust devils and global storms influenced by its own rotational dynamics, while the gas giants use their rapid spinning motion to create the banded atmospheric structures that give them their distinctive appearances. This rotational influence extends even to the most distant worlds. Uranus, spinning on its side through space, creates seasonal patterns that unfold over decades as different hemispheres alternately face toward and away from the distant sun. Neptune's rotation helps organize its supersonic winds into coherent patterns, despite the planet's incredible distance from any significant energy source. Each world's spin rate becomes a fundamental ingredient in its atmospheric recipe, determining how energy distributes across its surface and how weather patterns organize themselves. The role of chemistry in creating diverse weather phenomena becomes even more apparent when viewed across the full spectrum of planetary atmospheres. Earth's oxygen-rich environment allows for weather cycles based on water in all its phases, creating the gentle precipitation and moderate temperatures that make life possible. But other worlds demonstrate how different chemical compositions can create entirely alien forms of weather, using the same basic physical principles. The hydrocarbon chemistry of Titan, Saturn's largest moon, creates weather cycles based on methane and ethane rather than water. Liquid methane rains from Titan's thick atmosphere, collecting in lakes and seas that experience their own forms of evaporation and storm systems. This represents a complete parallel to Earth's water cycle, but operating at temperatures so cold that water would be frozen solid as rock. The sulfur compounds in Io's thin atmosphere create weather phenomena driven by volcanic activity rather than solar heating. Sulfur dioxide snow falls on this remarkable moon, while sulfur-bearing gases create colorful atmospheric displays that change in response to Jupiter's powerful gravitational influence. Even in the vacuum-like conditions of Io's exosphere, recognizable weather patterns emerge, demonstrating how atmospheric dynamics can operate even in the most seemingly hostile environments. These chemical variations remind us that weather is ultimately about the behavior of matter under different conditions of temperature, pressure, and energy input. The specific molecules involved, whether water vapor, sulfuric acid, methane, or exotic compounds we've never encountered on Earth, all respond to the same fundamental forces of thermodynamics and fluid dynamics that govern atmospheric behavior throughout the universe. The energy sources that power weather systems across the solar system tell their own fascinating story of cosmic diversity. Earth's weather draws its energy primarily from solar radiation, creating the temperature gradients that drive our familiar patterns of wind, precipitation, and seasonal change. But we've seen how other worlds tap into entirely different energy reservoirs to power their atmospheric dynamics. The gas giants derive much of their meteorological fury from internal heat sources, primordial energy left over from their formation billions of years ago. This internal heating creates weather patterns that operate independently of solar influence, allowing these distant worlds to maintain incredibly active atmospheres despite receiving only a tiny fraction of the sunlight that warms Earth's surface. Tidal heating, generated by gravitational interactions between moons and their parent planets, creates yet another form of energy that can drive atmospheric phenomena. The constant flexing and stretching caused by tidal forces generates heat that can power volcanic activity, atmospheric circulation, and even the sublimation of surface materials into thin atmospheres. Even the decay of radioactive elements within planetary cores contributes to the energy budget that drives weather on some worlds. This deep, internal source of heat operates on geological timescales, providing a steady energy input that can maintain atmospheric activity for billions of years, long after other energy sources have diminished. The magnetic fields that surround many planets add layers of complexity to weather systems that we're only beginning to understand. These invisible force fields, generated by electrical currents deep within planetary interiors, create protective bubbles that shape how the solar wind interacts with planetary atmospheres. The aurora displays that dance through Earth's polar skies represent just one visible manifestation of these electromagnetic weather phenomena. Jupiter's incredibly powerful magnetic field creates a magnetosphere so large it could contain several Earth-sized planets. Within this magnetic cocoon, charged particles from the solar wind interact with gases from Jupiter's moons to create radiation belts, plasma streams, and electromagnetic storms that represent a form of weather operating on scales and using energy sources completely foreign to terrestrial experience. The seasonal cycles that govern weather patterns across the solar system operate according to the same orbital mechanics that determine how much solar energy each hemisphere receives throughout a planet's year. But the incredible diversity in orbital periods, axial tilts, and distances from the Sun creates seasonal patterns that range from Earth's familiar four-season cycle to extremes that challenge our imagination. Mercury, with its highly elliptical orbit and lack of axial tilt, experiences seasonal variations based entirely on its changing distance from the Sun, rather than hemispheric differences in solar heating. Venus, shrouded in its thick atmosphere, shows virtually no seasonal variation at all, maintaining hellish conditions year-round regardless of orbital position. Mars experiences seasons similar to Earth's in some ways, but each season lasts nearly twice as long due to the planet's more distant orbit. These extended seasons create weather patterns that unfold over timescales that dwarf most earthly meteorological phenomena, with dust storm seasons and polar ice cap variations that stretch across many Earth months. The gas giants, with their complex systems of moons and their own sources of internal heating, experience seasonal changes that affect not just their own atmospheres, but the entire systems of worlds that orbit them. Saturn's changing orientation relative to the Sun influences not just the planet's own weather patterns, but also affects the atmospheric dynamics of moons like Titan, creating seasonal variations in hydrocarbon precipitation and atmospheric chemistry. Perhaps most remarkably, our journey through the solar system's weather has revealed how atmospheric systems can serve as windows into the deep history and future evolution of planetary environments. The current weather patterns we observe on each world tell stories that stretch back billions of years and forward into an equally distant future. Venus's current hellish conditions likely resulted from a runaway greenhouse effect that transformed what might once have been a more Earth-like world into the acid rain nightmare we observe today. The weather on Venus isn't just a current phenomenon, it's a warning about how atmospheric chemistry can spiral beyond the point of no return, creating permanent changes that persist for geological ages. Mars's thin atmosphere and subdued weather patterns hint at a world that once possessed a much thicker atmosphere capable of supporting liquid water on its surface. The current dust storms and seasonal ice cap variations are pale echoes of what might once have been a much more dynamic and Earth-like climate system. The gas giants preserve within their atmospheres chemical signatures and dynamical patterns that date back to the solar system's formation. The Great Red Spot of Jupiter and the hexagonal storm at Saturn's pole represent weather systems that have persisted for centuries or longer, maintaining their structure across timescales that span multiple human civilizations. Even Earth's current climate represents just one moment in a long history of atmospheric evolution. Our planet's weather systems have changed dramatically over geological time, from the oxygen-poor atmosphere of the early Earth to the ice ages that have periodically transformed our world's climate patterns. Understanding weather on other planets helps us recognize that Earth's current atmospheric conditions, perfect as they seem for life, represent a temporary balance that has evolved over billions of years and will continue changing into the distant future. As we contemplate these vast scales of time and change, we begin to see weather not just as a day-to-day phenomenon, but as one of the fundamental processes that shape planetary evolution itself. Atmospheric systems transport heat, redistribute materials, and create chemical reactions that can alter the composition of entire worlds over geological time. The erosion caused by Martian dust storms has helped sculpt that planet's surface features over millions of years. The chemical reactions occurring in Venus's sulfuric acid atmosphere continue to modify the planet's surface composition. Even Earth's gentle weather systems play crucial roles in the rock cycle, the carbon cycle, and countless other processes that maintain our planet's habitability. This long-term perspective reveals weather as one of the great creative forces in the universe, capable of transforming dead balls of rock and gas into dynamic, evolving worlds with their own unique characteristics and histories. The diversity of weather systems we've observed across the solar system demonstrates the incredible creativity of natural processes operating under different initial conditions and environmental constraints. From the elegantly simple temperature cycles of Mercury to the mind-bendingly complex atmospheric dynamics of the gas giants, each world has developed its own atmospheric personality, shaped by the interplay between its physical properties, chemical composition, and energy environment. No two planets share identical weather patterns, yet all operate according to the same fundamental physical principles. As our cosmic journey through the weather systems of the solar system reaches its peaceful conclusion, we're left with a profound appreciation for both the incredible diversity of atmospheric phenomena that exist beyond Earth and the remarkable balance of conditions that makes our home world such a perfect haven for life. The alien weather patterns we've explored, from Venus's acid rain to Neptune's supersonic winds, from Jupiter's ancient storms to Saturn's geometric tempests, all serve to highlight just how precious and rare Earth's gentle climate truly is in the cosmic context. Our world's weather systems operate within precisely the narrow range of conditions that allow liquid water to exist, temperatures to remain moderate, and atmospheric chemistry to support the incredible diversity of life that surrounds us. Tonight, as you prepare for sleep beneath Earth's protective atmospheric embrace, you can rest knowing that you're cradled by the most perfect weather system in the known universe. The gentle breeze that might stir your curtains, the moderate temperature that keeps you comfortable, the stable atmospheric pressure that allows you to breathe easily, all of these represent cosmic rarities that make Earth an oasis of habitability in an otherwise hostile solar system. The weather outside your window, whether it brings clear starlit skies or gentle clouds drifting through moonlight, connects you to processes that operate throughout the cosmos while maintaining the delicate balance that makes life possible. Every breath you take, every comfortable moment you experience, every sunrise and sunset you witness, all depend on the miraculous atmospheric conditions that make Earth unique among all the worlds we've visited in our cosmic journey. Sweet dreams, fellow traveler through this solar system of infinite atmospheric wonders. May your rest be as peaceful as Earth's perfect climate, as gentle as our world's nurturing weather systems, and as harmonious as the cosmic balance that makes our blue marble the most extraordinary weather laboratory in the known universe. In the quiet moments between wakefulness and sleep, as your breathing settles into its natural rhythm, let your mind drift back through our cosmic journey one final time. We've traveled billions of miles through space and time, witnessing weather phenomena so extraordinary they challenge everything we thought possible about atmospheric dynamics. Each world we've encountered has whispered its own secrets about the fundamental forces that shape reality itself. From Mercury's blazing days that melt lead to its nights colder than liquid nitrogen, we've seen how the absence of atmosphere can create the most dramatic temperature swings in our solar system. The thin wisps of Mercury's exosphere dance with particles blasted from rock by solar radiation, creating auroras that shimmer in the cosmic void. Venus revealed itself as a world where chemistry has run completely wild, where beautiful white clouds hide an atmosphere so corrosive it would dissolve metal in moments. Those elegant streamers of sulfuric acid that never reach the ground teach us about the delicate balance between atmospheric composition and planetary habitability. The greenhouse effect that makes Venus hotter than worlds closer to the Sun serves as a stark reminder of how quickly atmospheric conditions can spiral beyond any possibility of recovery. Our own Earth, viewed from this cosmic perspective, emerges as something almost impossibly precious. The water that falls as gentle rain, the oxygen we breathe so effortlessly, the moderate temperatures that make life flourish, All of these represent a convergence of conditions so rare they seem miraculous when compared to the hostile environments that dominate every other world in our solar system. Mars showed us weather as a sculptor of worlds, where dust storms can grow until they swallow entire planets, and where seasons stretch across timescales that dwarf human experience. The carbon dioxide snow that falls through its thin atmosphere and the geysers that shoot from its polar ice caps during spring thaw demonstrate how the familiar processes of weather can operate under conditions utterly foreign to earthly experience. The gas giants opened our eyes to weather as a cosmic force, operating on scales that humble any terrestrial comparison. Jupiter's Great Red Spot, that ancient storm larger than our entire planet, has raged for centuries, powered by heat flowing from the giant world's interior. The geometric perfection of Saturn's hexagonal tempest challenges our understanding of how atmospheric forces can organize themselves into patterns of mathematical precision. The ice giants at the edge of our solar system taught us that weather doesn't require warmth or familiar conditions to create phenomena of stunning beauty and terrible power. Uranus, tilted on its side and experiencing seasons that last for decades, shows us meteorology operating on timescales that challenge human comprehension. Neptune, with winds that scream at supersonic velocities through an atmosphere colder than frozen nitrogen, demonstrates that the most extreme weather in our solar system exists in the coldest, most distant realms. But perhaps the most profound revelation of our journey is how all these diverse atmospheric phenomena emerge from the same fundamental principles. The forces that create Earth's gentle trade winds operate according to the same physics that power Jupiter's centuries-old storms and Neptune's supersonic atmospheric rivers. Heat-seeking equilibrium, matter responding to pressure differences, rotation creating circulation patterns. All of these processes connect every world we've visited in an intricate web of cosmic relationships. The magnetic fields that surround many planets blur the line between atmospheric science and space physics, creating phenomena like Mercury's plasma tornadoes and Earth's auroras that remind us weather extends far beyond the simple movement of gases. Even the solar wind itself acts as a form of interplanetary weather, carrying the sun's influence to every corner of our cosmic neighborhood. This universal nature of atmospheric dynamics means that understanding weather on distant worlds helps us better appreciate the delicate balance that makes Earth's climate so perfectly suited for life. Our world's weather systems don't operate according to different laws of physics, but rather represent a unique combination of conditions that has created the most hospitable environment in the known universe. The seasonal changes that bring spring flowers and autumn leaves to our world, the rain that nourishes our forests, the snow that blankets our winter landscapes, all of these participate in the same cosmic dance of matter and energy that creates the hellish acid storms of Venus and the supersonic winds of distant ice giants. What makes Earth special is not the absence of extreme weather, but the way our atmospheric systems maintain perfect balance within the narrow range of conditions that life requires. As you settle deeper into the comfort of your earthly sanctuary, surrounded by air you can breathe and temperatures that keep you perfectly comfortable, remember that you're experiencing something extraordinarily rare in our solar system. The gentle weather that cradles our world represents the culmination of billions of years of planetary evolution, a masterpiece of natural engineering that has created conditions so ideal for life they seem designed by some cosmic architect. Every cloud that drifts across our sky connects us to the larger patterns of atmospheric dynamics that operate throughout the universe. Every raindrop that falls to Earth participates in processes that link our world to the vast community of planets and moons that share our solar system. The weather outside your window tonight, however calm or dramatic, represents part of the same cosmic symphony that includes Saturn's hexagonal storms and Jupiter's ancient tempests. But while those alien weather systems inspire awe and wonder, they also serve to highlight just how precious our own atmospheric conditions truly are. The moderate temperatures, the breathable air, the life-giving precipitation that characterizes Earth's climate represents something so rare and valuable it defies description. We live within the embrace of the universe's most perfect weather system, where atmospheric forces serve life rather than destroying it. In the gentle rhythm of your breathing tonight, you participate in the same exchange of gases that creates weather patterns across the cosmos. The oxygen you inhale was once part of ancient atmospheres, cycled through countless weather systems over geological time. The carbon dioxide you exhale will become part of future atmospheric dynamics, contributing to the ongoing dance between matter and energy that shapes our world's climate. This perspective transforms every breath into a connection with cosmic processes that extend far beyond our planet's boundaries. You are not separate from the weather systems we've explored, but part of them, a temporary arrangement of cosmic matter that has achieved the remarkable feat of consciousness and can contemplate the very atmospheric processes that make your existence possible. The atoms in your body were once part of stellar atmospheres, scattered by ancient stellar winds and incorporated into the solar nebula from which our entire planetary system formed. The water in your cells has cycled through countless weather systems across billions of years, falling as rain on ancient continents, flowing through primordial oceans, and rising as vapor into prehistoric skies. Tonight, as you rest beneath Earth's protective atmospheric blanket, you are cradled by weather systems that represent something truly miraculous in the context of our cosmic journey. The air that surrounds you, the moderate climate that keeps you comfortable, the stable atmospheric chemistry that makes life possible. All of these are gifts of cosmic rarity that make our blue marble the most extraordinary world in our solar system. The stars that shine through Earth's transparent atmosphere tonight have witnessed the birth and evolution of countless weather systems across billions of years of cosmic time. They have seen worlds transform from hostile wastelands into gardens of life, and others spiral into atmospheric chaos that renders them uninhabitable. They shine down now on a world where weather has achieved perfect balance, creating conditions so ideal for life that consciousness itself has emerged to contemplate its place in the cosmic order. As sleep carries you gently away, let your dreams be filled with the wonders we've discovered together. Picture the ancient storms that rage across Jupiter's colourful face, the elegant geometry of Saturn's polar tempest, the supersonic winds that race through Neptune's frozen atmosphere. But also dream of the perfect balance that makes Earth's weather the foundation of everything beautiful and alive in our corner of the cosmos. May your rest be as peaceful as a summer evening's breeze, as refreshing as morning rain on thirsty soil, and as harmonious as the cosmic forces that have conspired across billions of years to create the most perfect weather system in the known universe. Sweet dreams, fellow traveler through this magnificent cosmos where weather dances across alien skies while cradling life itself in its gentle, nurturing embrace. Itself in its gentle, nurturing embrace. As we reach the end of our gentle drift through the cosmos, floating peacefully back toward our blue marble home, we carry with us something profound and transformative. We've witnessed weather systems that challenge every assumption we've ever held about what's possible when matter and energy dance together across the vast scales of space and time. From Mercury's blazing furnace days to its nights colder than interstellar space, from Venus's eternal acid rain that never touches ground to Mars's planet-swallowing dust storms, from Jupiter's centuries-old tempests to Saturn's impossible hexagonal perfection, from Uranus's decades-long seasons to Neptune's supersonic winds screaming through frozen darkness, we've seen that weather is far more than simple meteorology. It's the fundamental expression of how universes organize themselves, how cosmic forces sculpt reality itself into forms both beautiful and terrible. Each world we've visited has whispered its own secrets about the delicate balance between creation and destruction, between order and chaos. The sulfuric acid clouds of Venus teach us about atmospheric chemistry spiraling beyond any hope of recovery. The great red spot of Jupiter demonstrates how weather systems can achieve a kind of immortality, persisting across centuries, while civilizations rise and fall on distant worlds. The geometric precision of Saturn's polar storm reveals that even in the apparent chaos of atmospheric dynamics, nature can create patterns of mathematical perfection that seem almost too elegant to be real. But perhaps the most profound revelation of our cosmic journey is how these alien weather systems illuminate the extraordinary preciousness of our own earthly climate. When viewed against the backdrop of supersonic winds, acid rain, crushing pressures, and temperatures that melt lead or freeze nitrogen solid, Earth's gentle breezes and life-giving precipitation emerge as something almost impossibly rare and valuable. The water that falls as rain in our gardens participates in the same fundamental processes that create methane storms on Titan and carbon dioxide snow on Mars. The clouds that drift peacefully across our skies form according to the same physical principles that generate the towering ammonia storms of the gas giants. Yet somehow, through a convergence of conditions so precise it seems miraculous, these universal forces have combined on Earth to create weather that nurtures rather than destroys, that supports the incredible diversity of life rather than creating wastelands of chemical hostility. Every breath you take tonight connects you to this cosmic story. The oxygen in your lungs was once part of ancient stellar atmospheres, scattered by stellar winds and incorporated into the planetary materials from which Earth formed. The carbon dioxide you exhale will become part of future weather systems, contributing to the ongoing atmospheric cycles that have maintained our world's habitability for billions of years. You are not separate from the weather systems we've explored together, but intimately connected to them. You are made of the same cosmic materials that create storms on Jupiter and winds on Neptune. The atoms in your body have participated in atmospheric dynamics across vast scales of space and time, cycling through countless weather systems before finding their temporary home in your consciousness. This perspective transforms our understanding of what it means to exist within Earth's protective atmospheric embrace. We're not simply observers of weather, but participants in the same cosmic processes that operate throughout the universe. The gentle climate that surrounds us represents the culmination of billions of years of planetary evolution, a masterpiece of natural balance that has created the most perfect conditions for life in the known cosmos. Tonight, as you rest beneath Earth's transparent sky, whether it brings clear starlight or gentle clouds drifting through moonbeams, remember that you're experiencing something extraordinarily precious. The moderate temperatures that keep you comfortable, the breathable atmosphere that sustains your life, the stable weather patterns that make our world habitable, all of these represent cosmic rarities that make our blue marble a true sanctuary in an otherwise hostile universe. The alien weather we've witnessed together serves not just to inspire wonder, but to deepen our appreciation for the miraculous balance that makes Earth home to everything we know and love. In understanding the atmospheric chaos of Venus and the frozen fury of Neptune, we gain a profound new respect for the gentle rains and moderate seasons that make our world a garden of life in the cosmic wilderness. As sleep carries you peacefully away, let your dreams be filled with the memory of our cosmic journey through realms of weather beyond imagination. But also let them be grounded in gratitude for the perfect atmospheric conditions that cradle you each night. The invisible forces that maintain just the right temperature, just the right pressure, just the right chemical balance to make consciousness itself possible. May your rest be as gentle as Earth's nurturing climate, as harmonious as the cosmic forces that have conspired across eons to create our world's perfect weather, and as peaceful as the knowledge that you exist within the embrace of the most extraordinary atmospheric system in the known universe. Sweet dreams, fellow traveler, in this magnificent cosmos where weather tells the story of worlds, and where our own blue marble stands as the most beautiful chapter in that eternal tale.